Okay, folks, so we're about to introduce the central limit theorem, and this will correspond to assignment 18. And again, I would ask that you download the PowerPoint. It's got the notes in it. It's got the examples and the notes. They're already filled in, so we can maybe go through that part a little faster since we don't have to stop and wait for you to write things down. Or again, you could always pause the video if you need to in order to get caught up. So anyway, obviously we should probably look at example number 1 here. So we have 10,000 people in a certain population, and we're told that the mean salary in that population is $35,000. I've got a visual here for you that's on one of the slides that was uploaded, and the standard deviation is 8,000. All right, so those salaries would be considered a variable, X, like all others. Okay, but see, the problem here is they don't tell us that it's normally distributed. In fact, I went out of my way to say that we don't know how these are distributed. So the problem is, you know, the graph of this could be anything, squiggly wiggly, all right? It's not a bell curve necessarily. So here's the visual that I would provide for you. And I guess the thing, before I do that though, let me talk about this. The key words in this question are the fact that we're taking a sample from that population, and we want to determine a probability related to the mean of that sample, all right? And so that actually changes the question. The probability that the mean of a sample, the symbol for the mean of a sample is not X. What is it? Anybody? That's right, it's X bar. That's right. Okay, so see, we're finding the probability that the mean of a sample, which is called X bar, that's an important thing to notice in this question. What's the probability that the mean salary for that sample of 30 workers is greater than 31,950? We're making a leap here into a different kind of question. All right, we're jumping over to a different sort of question here, and that's important to notice. When we're finding a probability related to the mean of a sample, and look, I'll just tell you this right now, on assignment number 18, that's what all these questions are going to involve. So you don't really necessarily need to learn to pick it out. It's going to be on all the questions on assignment 18, central limit theorem. You're going to be asked to find the probability related to the mean of a sample, all right? And therefore you're going to apply this theorem that we're about to introduce. X bar, that is critical that we notice that. All right, so if you would go to the notes, it says example number 1 continued. I have a visual here that I hope will help you understand this. So these salaries, actually X, I didn't plan very well on that, but that's our population X, our original population, and we were told that we did not know how it was distributed. There's my squiggly wiggly on the board, all right? But again, we made a jump here. We made a leap, a jump, because when the problem said that there was a sample and we're going to calculate a probability related to the mean of that sample, we jumped over to the distribution called the distribution of sample means, X bar. That's an important thing to notice here. On assignment 18, they're all going to do this, okay? So anyway, now, let's backtrack just a little bit. We were told that original population had 10,000 workers. And here's what I would ask you to think about. You don't have to do this calculation to work this question, but here's the deal. If you had a sample of 10,000 people and you chose any 30 of those people to constitute your sample, wouldn't that be a combination? So the point is, if you take the combination of 10,000 choose 30, that's like 3.6 times 10 to the 87th power. Move that decimal 87 places. The point is, there's a huge number of samples of size 30 that you could possibly select from a population of 10,000. And every one of these samples over here would have a mean, all right? And this is what this distribution represents. The means for every possible sample of size 30 that you could choose from a population of 10,000. It's vast, it's huge, all right? So it's more of a theoretical set of numbers over here. But this theorem we're about to talk about, a lot of really smart math people figured out this theorem that applies to a situation like this, and we're going to take advantage of their work. So, it turns out that when we make that jump over to the distribution of sample means, here's the deal. We were given the mean and the standard deviation for that original population, but when the question made reference to a probability related to the mean of a sample, we have to realize that we're making that jump over there to that X bar, all right? That distribution of sample means. We're jumping over there, all right? The mean of a sample, jump, all right? And I'll put this up in more general terms here in a minute. It's on another slide that you have. But the smart math people figured out the following relationship. The mean for this distribution that we just jumped over to, all right, called mu subscript x bar, is found by taking the mean of the original population. So they're the same. So that's easy. They're always equal, all right? Whatever this one was, that one was. Let me pull this down here. Sorry, I didn't plan ahead the best here. So the mean of the original population was 35,000, and so the mean of the distribution of sample means is the same, and it always will be, all right? But the standard deviation for this new distribution is different, and it's this little formula that some really smart math people figured out. And here's what they discovered. The standard deviation for this distribution, sigma x bar, not to be confused with the original sigma, is always given by the formula sigma over the square root of n, where n is your sample size. So you take the standard deviation of the original population, you divide it by the square root of your sample size, which I want to remind you they sampled 30 workers, and that crunches out to be this number, 14,000, and so on. Okay, so far so good, hopefully. And it's important to notice that we jumped over to this distribution when the question mentioned the probability that the mean of a sample, x bar, all right? So, the standard deviation changes. There's a new standard deviation in town. Yeehaw, right? I guess we'll put that on. There's a new standard deviation in town, right? Okay, now, but here's where it gets really exciting, okay? We didn't know how the original population was distributed, but you know what? The smart math people figured out that as long as your sample size is 30, if you sample at least 30, if n is greater than or equal to 30, that will indeed be a bell curve over there, okay? So this distribution of sample means is indeed normally distributed, all right? So even though the question did not mention normally distributed, two things happened that are going to allow us to proceed with a normal bell curve now. The first thing that occurred is the probability that the mean of a sample, x bar, all right? And the other thing is we sampled at least 30. That's the statistical cutoff. So we're allowed to put a bell curve here. Wow! All right, so that thing kind of looks like a bell curve now, doesn't it? I don't know if this works. Sorry. I didn't really rehearse this very well, but anyway. See, now we're looking at a bell curve, aren't we? All right. So, I'm going to have to take this off because I can't hear you guys very well when you ask me questions and things, but maybe we'll put it back on. And again, ask your parents about Beldar and all that. Okay, cone head, bell curve head. All right. So anyway, that's awesome. We now have a normally distributed set of numbers. We have the mean of 35,000. Guess what? We can now finish the question off as we have done on previous assignments. So the probability that x bar, not x, right? We left our x and ran off to the x bar, all right? Make up your own punchline there. But anyway, 31,950 is below the mean. Greater, that would be all that area there, okay? We got a bell curve, we've got a mean, standard deviation, we've got a shaded region, and now basically this is the same thing as what we've seen before. So, and I didn't have a lot of board space here because of the confines of this, but what you would hopefully remember is that we would change that into z, all right? And we're going to draw draw a new picture here. Standard normal, bell curve 0 in the middle. Let's mimic that right there, okay? And we standardize that score, right? I'm really sorry I didn't plan ahead the best here. But again, that 31,950, if you want to make it into a z-score, would be x minus mu. This is just like assignment 17 that we did earlier, divided by sigma. A lot of moving parts here, guys. A lot of links. I don't have them all linked up the best I could, but I did what I could. But I just want to remind you, you standardize this like we did on assignment 17. X minus mu over sigma. Now, the key mistake I see all the time is when you're applying the central limit theorem, remember to use the new sigma, right? There's a new sigma in town. When you apply this, you're not using the original sigma. There's a new sigma in town, right? There's a new standard deviation, all right? And it's this number. So then, and that's the key element here when you standardize that score. And it turns out that that is negative 2.09. Okay, so we're on assignment 18, central limit theorem. When they mentioned x bar, that allowed us to use the bell curve. This now became assignment 17. After we standardized it, guess what this is now? Assignment 16. We want to know that area there. So we got ourselves a bell curve, we've got a shaded region, and we come over here and we go, hey, how you doing, table? And here we go again. We got to do this, right? Table time, right? So we look up the 2.09. This is assignment 6. Oh, this is assignment 16. So 2.09 is 2.09. I hope you remember how to do this. 0.4817. And 0.4817, recall, would be that middle sliver right there. And then according to this picture, we would have all these numbers up here as well, the upper half of the bell curve. And so 0.4817 plus 0.5, 0.9817. Answer, 0.9817. All right, so now it's my job to just hopefully try to put this all together, and we'll give you the theory in general, but I just want to throw it out this way. Let me try to explain this now. If you took this vast number of samples of size 30 that could be chosen from a group of 10,000 and found the mean for every one of those, all right, about 98% of those samples, of all those samples, would have a mean greater than 31,950. All right? So that's how that would apply to this specific question. Now let's look at the theorem in general. All right? We're going to start putting in some of the generalities about this theorem. And this is, again, a slide that was given to you. It says central limit theorem continued with a couple circles on it. All right? So see if you can find that one or hit pause right now while you're looking for it. But the theorem in general would be this. If you have a population called X, all right, but the question wants you to determine a probability related to the 1, 2, 3 mean of a sample, which is called X bar, all right, that's important if that's in the question. And it will be on every question on assignment 18, okay? So you don't even really have to determine that necessarily. You would if we took the test over this though, so you're lucky. But anyway, if you had a mean and a standard deviation of your original population, all right, but you jumped over there, you left your X and you jumped over to the X bar. You left your X and went to the X bar, all right, then your mean and your standard deviation are given by these two formulas. Mean equal, that's easy. Standard deviation, that formula, sigma over the square root of your sample size, n, all right? So those things are in place. Oh, you only apply this theorem, though, if you're talking about the mean of a sample, which was not done on the previous assignments, but it is now, all right? But anyway, no matter how your original population is distributed, that's just a generic squiggle wiggle That was the rainfall in Wettville, if you remember, not a bell curve, basically. But the theorem says that if your sample size is at least 30, and it is, we sampled exactly 30, then this is normally distributed. So, what happens for us to use the central limit theorem? What has to happen? We're finding a probability related to the mean of a sample, not x, x bar, jump over to x bar. And if we sample at least 30, bell curve, yay. Now you might wonder, what happens if we don't sample at least 30? You already have it printed there in front of you, so let's talk about that. If we know that the original distribution is a bell curve, if we're told that the original population is a bell curve normally distributed, then it doesn't matter how big the sample is. See, no restrictions. This is automatically a bell curve. All right? So, where would the theorem not be applicable in my mind? Well, if we did not know how the original distribution was, and we sampled less than 30, this theorem wouldn't work. That's basically that, okay? So just keep that in mind. And so just remember, x bar, mean of a sample, you'll jump over. And that's what happened in this question, right? We jumped over because we were finding the probability related to the mean of a sample. And again, we sampled at least 30. So I did my best with the theorem in general. I hope that made sense. And now we'll practice 1, 2, 3, 4 more of these, all right? All right, thank you very much. Woo! Good job.